In this video, we will show that from an existing component, it is possible to make changes and generate new components with different functionalities, better suited to the culture of different energy utilities. Our starting point will be the substation component, shown in the previous video. To do this, initially, we will create a new application, called Component Change, and import the substation component. Once the component is imported, as shown before, there is already an example bay, called SPF_11F1. Let's copy this bay and paste it on a screen. Now, we will duplicate the bay SPF_11F1. When we click on the bay, we observe that it is associated with the SPF_11F1 object. On the duplicated bay, with a click on the right mouse, we will select the option to unmake. As we can see, the bay symbol is composed of dozens of symbols, where each symbol has one or more dynamics, associated with the tag value of the FDDW template, mapped to the SPF_11F1 bay. We copied the symbols associated with the circuit breaker, and verify that this group is made up of 7 symbols. Let's check the dynamics associated with each of these symbols. The circuit breaker has 3 dynamics. The first, when we double-click on it, with the left mouse button, move 4 reference variables shown on the screen, and calls the circuit breaker command window. Other dynamic, the fill color, change the color of the symbol, according to the value associated with the circuit breaker. The red rectangle, around the circuit breaker, becomes visible when the locked attribute, associated with the circuit breaker, becomes 1, informing that it is blocked. The letter L becomes visible when the P43 rem tag becomes true, indicating that the circuit breaker is in local. The symbol of alarm disable becomes visible when the attribute alarm disable, associated with the circuit breaker, becomes 1. The symbol of circuit breaker disable becomes visible when the attribute disable, associated with the circuit breaker, becomes 1. The circuit breaker manual flag becomes visible when the value of the tag DJ52IMP is equal to 1. The circuit breaker live line flag becomes visible when the value of the tag DJ52IMP is equal to 2. In the same way that the dynamics associated with the circuit breaker were shown, other dynamics associated with other symbols on the screen will work in a similar way. We will activate the program only with the display options and scripts, and we will change some tags and their attributes, operationalizing some of the dynamics we have just seen. Initially, using ActionNET's IntelliSense functionality, we selected the D52_AA tag. On the watch and change its value to 2, close circuit breaker. As shown, there are dozens of attributes associated with a tag. We change the value attribute to 1, opening circuit breaker. We change the alarm value attribute to 1, and the disabled alarm symbol becomes visible. We change the disable attribute to 1, and the disable equipment symbol becomes visible. We change the locked attribute to 1, and the red rectangle becomes visible, informing locked equipment. After this introduction showing how symbols work on the screen, let's make some changes to the component. In this component, we have 5 types of bays: capacitor bank, feeder, line, transfer and transformer bays. If we want, for example, to change the address of one or more input and output tags of a template, just go to it, and change the address of the points we want to change. As the addresses are in the comment, and the alarm types are in the category, when entering the template, we must enable these 2 columns. At category, we have several attributes, used by the deploy, such as type of alarm, if the point goes to history, etc. As an example, we will change the type of alarm, associated with the change of state of the circuit breaker, saying that in addition to going to events, it should also go to alarms. At comments, we have the point access type, its side address, in this case using the IEC 61850 protocol, and its alarm priority. We can change any of these attributes in the template, changing for all bays of this type. For example, let's say that the type of relay, associated with the bay, has changed, and there is a small change in the address string. They sent us the ICD of the new relay. And through the program IED Explorer, we read this new ICD. And we verified the address changes of the feeder's circuit breaker, changing it in the template. We can also change the alarm priority. In short, through comment and category, we could change several attributes of the points, as shown. When we change these attributes in the bay type template, the change will be for all applications using this component as a startup. If, however, we wanted to change the address attribute of a given bay, after the deploy explosion, we must go to Device, Points and change the specific address. ActionNET has several symbol libraries, and you can create as many as you want. We will open the library called Bays, and we will load some of its symbols, and generate a single line diagram. In this case, we carry a feeder bay, a transformer bay, a line bay and 2 double bars, one for low voltage lines, and one for high voltage. We quickly set up the substation diagram. In the sequence, we will edit the feeder bay. Inverting the current with the navigation button for the bay detail screen. We also alternate the relay curve adjustment buttons. When saving the changed bay, this change is valid on all screens where the bay appears, as well as in the library. Like this change, any other bay change could be done. That is, from a ready-made and tested component, it is much easier to generate a new component, more suited to the user's culture. All the screens of the substation component were based on ESA recommendation to high-performance HMI. On the other hand, several utilities had their own standard, and a very common electrical utility practice is to use the voltage value as a reference for the bays and bar color. The substation component doesn't need to be changed to adopt this practice, as we will see next. The ZDist object has several tags, used to control the application's functionality. At its template, the highlighted object will define how the lines will be colored by voltage level. This object will have a sub-template, with as many variables as the voltage levels shown in the single line diagram. In this case, we have two voltage levels, bay color 1, and bay color 2. If the value attribute of these tags is equal to 0, they will keep this gray color. If equal to 1, they will have the color shown in the comment attribute, associated with the variable, as we will show then, during application execution. Using the watch tool, we will assign 1 to the value attribute of the bay color 1 and 2, respectively. And the colors associated with its comment attribute are moved to the color of the lines of all voltage level elements. If we wanted to change the colors of the voltage level, just change the attributed comment of the bay color 1 and 2. If, in the single line diagram, there are 3 voltage levels, a new tag, called bay color 3, must be created, and the respective bay symbol must be included in the symbol library. Let's now see how select colors from the color spectrum to associate to the line's voltage level. In the drawing area, we create a rectangle, and after we open a window, to manipulate the color spectrum of the rectangle, pressing the fill button. The highlighted area is in hexadecimal, the color associated with the rectangle, and over it, we paste a string that corresponds to the gray color, changing the color of the rectangle to this tone, which is the tone of all the lines. Now we go to the screen of object bay colors 1 and 2, and we copy the hexadecimal string of bay color 2, and we go back to the screen, where we paste this string in the color of the rectangle, changing its color to red. Just like we did with bay color 2, we can do it with bay color 1, and, if we want to change the bay color 1 and 2, just change the comment attribute to a new color. So, this is how we adjust the colors of the single line diagram to utilities culture. Just as we can change the symbol library and a symbol's functionality, such as its color, we can change any detail screens of a bay, create new screens from an existing one, change command windows, etc. Let's change a details screen, and then change a bay symbol to call this screen. The first feeder bay is associated with the SPF11F1 object, the second one is not associated to an object. We will also associate it with the SPF11F1. Now let's run the application and observe that the two feeders are associated with the object SPF11F1 and have their navigation buttons identified, and when we click on it, the variables of this object will be mapped in the detail screen. Once this is done, we will stop the program and change the feeder detail screen, change its name and change the second feeder to call this screen, instead of the default screen. Let's say that this new feeder doesn't have relay curve adjustment buttons, as well as don't have goose failure alarm. We also will insert a button on the screen to return to the main screen. In fact, we could change the entire layout of the screen, thinking, for example, that this protection feeder relay is from another manufacturer, with fewer functionalities. Now, we are going to unmake the second feeder symbol, remove the navigation button. Move the current value to the location of the removed button, and we will create a different button to navigate to this new detail screen. In the end, we will make a new symbol for this special feeder bay, called FTDW1, and we will include it in the base symbol library. To finish, let's run the application and verify that when we navigate through the first feeder, we go to the existing screens. If we navigate through the second feeder, we navigate to the new screen, where we have made some changes. If we save this new component with the culture of a second customer or, for example, with a new family of relays, or new manufacturers. Concluding, this video showed that, from a first component, which contains all the facilities to generate a substation, using the culture of a given electricity utility, we can generate a second component, with different functionalities, to adapt to the culture of a second utility. Over time, we will have libraries, with the culture of several energy utilities. Parameterization, factory testing and commissioning will occur without surprises, from the point of view of SCADA.